Can you spot cycles before they wreck a project? Course Schedule is a Pattern Mastery 100 classic. Frequently asked at Google, Amazon, and Meta for its blend of graph, topological sort, and cycle detection. Over 40% of candidates either miss edge cases or get tangled in the graph logic. If you master this, you'll ace any dependency or order check problem in interviews. Let's break down Course Schedule with the basic method, a stepwise approach that builds deep understanding for any cycle or topological ordering question. Let's break down the problem. You're given num courses, number of courses, and a list of prerequisite pairs. Can you finish all courses? Each pair, A, B, means, to take course A, you must first finish course B. The courses form a directed graph. Your task is to check if there's any cycle, which would make it impossible to finish all courses. Integer num courses list of prerequisite pairs. Boolean. True if all courses can be finished, false otherwise. Think of project tasks or college courses, where some steps must happen before others. Interviewers might ask, how would you check for circular dependencies in a build system or workflow manager? What's tricky? You need to detect cycles in a directed graph, classic topological sort. Multiple valid orderings may exist. Must efficiently track visited nodes and recursion stack. Build an adjacency list to represent course dependencies. Use DFS to detect cycles. Mark each node as not visited, 0 visiting, 1 visited, 2 for each node. If already fully visited, skip. If visiting, and you re-enter it, you found a cycle. Recursively DFS all neighbors. If any cycle is found, return false. Otherwise, return true. Let's clarify. The recursion stack, visiting, is key. It tracks the current path. Alternatively, BFS, Kahn's algorithm, with indegrees works as well, but DFS is easier to explain in interviews. Edge cases. No prerequisites. Always return true. Disconnected graph. Some courses with no dependencies. Multiple cycles. Build adjacency list from prerequisites. Initialize state array for all nodes. For each node, DFS. If node is visiting, return false, cycle. If node is visited, skip. Mark as visiting. DFS all neighbors. After neighbors, mark as visited. If no cycles, return true. Let's try to implement it using solution 1. Time complexity. Num courses plus prerequisites. Length. The concept discussion. We're solving course schedule by modeling courses as a directed graph. An arrow goes from a prerequisite to the course it unlocks. Then we run DFS, depth first search, to detect cycles. A cycle means this course depends on itself indirectly, so it's impossible to finish. To catch cycles, we track each course in one of 3 states: not visited yet, currently in the DFS path, or fully completed. If we ever re-enter a course that's currently in the path, that's a cycle. Alright, this can-finish function is the full solution. It takes the number of courses and a list of prerequisite pairs, and its job is simple. Return true if we can complete everything, or false if there's a dependency loop that makes it impossible. First, we build a graph. Think of graph X as, what courses become available after I finish course X? So for each pair, course, prereq, we add an arrow from prereq to course. That way, from a prerequisite, we can quickly see what it unlocks next. Next, we create a visited array to track progress for every course. We use 3 states. 0 means we haven't touched it yet. 1 means we're currently exploring it in the DFS path. 2 means we've fully explored it and confirmed it's safe. This is the key idea that lets us detect cycles reliably. Now we define the DFS helper. This function tries to confirm, starting from this course, can I follow the dependency paths without getting stuck in a loop? Here's the big logic. If we hit a course marked visiting, state 1, we've looped back into our current path, that's a cycle, so we return false. If we hit a course already marked visited, state 2, we already proved it's safe earlier, so we can skip the work and return true. Otherwise, we mark the course as visiting, explore everything it leads to, and if all paths are safe, we mark it visited and return true. Finally, we run DFS starting from every course. Why do we do that? Because the graph might have multiple disconnected parts, like separate groups of courses that don't relate to each other. If any DFS call finds a cycle, we immediately return false. But if every course checks out clean, then no cycles exist anywhere, and we return true. And that's the full picture. Build the dependency graph, track states, use DFS to detect cycles, and verify every course can be processed safely. And that's how this algorithm works. It first builds the dependency graph and initializes the visit states, then runs DFS with cycle detection across all courses to confirm no circular prerequisites exist. Efficient, simple, and elegant. Alright, let's test our function with this input. Num courses equals 2 and prerequisites equals 1, 0. This means we have two courses, 0 and 1, and the pair, 1, 0, tells us, to take course 1, you must first complete course 0. Now we build a directed graph from prerequisites. So we create an edge 0, 1, because course 0 unlocks course 1. Then we run DFS to check for cycles. If we ever revisit a node that's currently being explored, that would mean a loop, and then finishing all courses would be impossible. In this case, starting from course 0, we go to course 1, and course 1 doesn't point back to anything. So we successfully finish exploring without detecting a cycle, which means the course plan is valid. And that's exactly what the program returns. True. That makes sense because you can simply take course 0 first, then course 1, and you're done. The code passes the test case. So, our implementation is correct. The algorithm successfully detects whether a cycle exists using DFS, efficient and accurate. Let's try to implement it using solution 2. Time complexity. Num courses plus prerequisites. Length. The concept discussion. This approach uses topological sort, Kahn's algorithm. The idea is to count how many prerequisites each course still needs before it can be taken. That's the indegree. Any course with indegree 0 is ready to go right now, so we put it into a queue. Then we repeatedly take a ready course, complete it, and reduce the indegree of the courses it unlocks. If we can process all courses this way, there's no cycle and we can finish. If we get stuck early, some courses never reach indegree 0. That means there's a loop somewhere. This can-finish function solves the problem by trying to take courses in a valid order. If we can keep picking courses that have no remaining prerequisites until we've taken them all, we return true. If not, we return false. First, we build two key tools. The graph tells us, after finishing this course, what courses does it unlock? The indegree array tells us, how many prerequisites does this course still need? Every time we see course, prereq, we add course to the list unlocked by prereq, and we also increase indegree course, because that course has one more required step before it can be taken. Next, we find all courses that are immediately available, meaning they have 0 prerequisites. Those are our starting points, so we push them into a queue. You can think of this queue as the list of ready-to-take courses. Now comes the core workflow. While we still have ready courses in the queue, we take one out, which represents completing that course. We increase count to track how many courses we've successfully completed. Then we look at the courses it unlocks. For each unlocked course, we reduce its indegree because one prerequisite has just been satisfied. If any unlocked course reaches indegree 0, it becomes ready, so we push it into the queue. That's how availability spreads through the graph. At the end, we check if we completed all courses. If count equals num courses, we successfully found an order to take everything, so true. If count is smaller, it means some courses never became available, usually because they're trapped in a cycle, so false. And that's how this algorithm works. It first builds the graph and indegree counts while collecting all starting courses with 0 prerequisites, then repeatedly processes ready courses and reduces indegrees to unlock new courses until it either completes all of them or gets stuck. Efficient, simple, and elegant. Okay, up next, let's run a real test on this one. We've got num courses equals 2 and prerequisites equals 1, 0, 0, 1. That means there are two courses, 0 and 1. But here's the problem. Course 1 depends on course 0, and course 0 depends on course 1. With Kahn's algorithm, we track indegree, which is basically how many prerequisites each course still needs before it can be taken. From the input, course 1 has prereq 0 so indegree 1 becomes 1. Course 0 has prereq 1 so indegree 0 becomes 1. So now indegree looks like indegree 0 equals 1. Indegree 1 equals 1. Next, we try to add courses with indegree 0 into the queue, meaning courses we can start immediately. But in this case, none of them have indegree 0. Both courses are waiting on each other. So the queue starts empty, the loop never runs, and count stays 0, meaning we couldn't complete any course at all. And that's why the function returns false, which matches the expected output. The result makes perfect sense because this prerequisite setup forms a cycle, so there's no valid order to finish both courses. So, our implementation is correct. The algorithm successfully uses indegrees and a queue to detect cycles, and when no starting course exists, it correctly concludes the schedule can't be completed. Alright, quick recap to wrap up course schedule. At its core, This problem turns courses and prerequisites into a directed graph. Each prerequisite pair basically says, you can only take course A after course B. So the real question becomes simple. Can we finish everything, or does the graph contain a cycle? Because if there's a cycle, that means the requirements loop forever, and finishing all courses is impossible. From there, we focused on the key insight: we only fail when dependencies loop back. So cycle detection is the entire problem. We also noted there are two solid ways to do that: DFS with state marking or BFS using indegrees, and we went with DFS because it's a direct and fast way to spot cycles. The plan was straightforward. Build an adjacency list from the prerequisites, then track each course using 3 states: unvisited, visiting, and visited. We run DFS from every course to handle disconnected parts of the graph. And the moment DFS reaches a node that's already marked visiting, we've detected a cycle. After setting up the graph and the state tracking, we ran the solution, and it executed cleanly on LeetCode with no errors. We also validated the logic through the LeetCode run, confirmed the behavior matched expectations, handled edge cases correctly, and all test cases passed. The big takeaway is that this problem is really a topological sort mindset. Schedules break when cycles exist. Once you can reliably detect cycles, you can reason about a lot of real systems, and a ton of graph interview problems start feeling way more manageable.